So thanks Tom Shen for joining this week. I'm excited to sort of go through your Sumcheck repo with you. For anyone who didn't catch the announcements, Tom Shen implemented the Sumcheck repo at Arkworks. So,
Yeah,
welcome,
yeah.
Tom Shen.
This is the paper I was referring when I wrote the Sumcheck. So here is the function that we want to prove. Basically, it's like a multilinear function where we have like a lot of variables, and we want to check that the sum of this function on the Boolean hypercube like equals to like equals to some field element. And what I implemented is kind of like this form. So basically, we have like one multilinear function and another multilinear function, and we can even have more, and they multiply together, and we want to check that the multilinear function, even in this form, can be like can be verified like in kind of linear time. So this is what I was doing, and here is like the main structure of the repo. So this one is like the one single library. There's no workspace here. And this one is the part for the multilinear sum check. And this is one for the GKR round sum check, which is kind of like a special form of this function, which is defined in, let me see. Yeah, this special form, which is quite useful for the GKR protocol. And now like here is the protocol. Basically, Sumcheck is an interactive proof protocol. So first we need to write this interactive proof. So we need to have the prover and the verifier. So the prover will have some rounds, and at each round, the prover will send like a polynomial represented in multilinear form, and the verifier will sample a random element and send to prover. So basically, the prover's message will be kind of like long, but the verifier message will kind of succinct. That is kind of like a convention in this protocol. And yeah, so first the prover will initialize. Basically, this one will give a prover state, which is the initial state. And then after that, the prover will do some round, and this round will take some prover state and the verify messages from this round and return like the prover message and the prover state, which is kind of like some communication protocol. And the verifier will kind of like do the similar thing. So verifier will have a state, and first the verifier will initialize the state using some polynomial information, which is contains like the number of polynomial and also like the number of multiplicants, like in the product of polynomial. And the verifier do not even need to know what is a polynomial. It just need to know like some structure for the polynomial. And then the verifier will do some round, like just like kind of like doing similar thing as a prover. So it takes some messages, some state, and some ing. And after this round, the verifier will have some special round on the last round. So it will take some state and the asserted sum, and the verifier will check, like to do all the check for the polynomial and output a subclaim. Basically, this subclaim will be correct if the original prover's claim is correct. So the verifier can then like verify the subclaim, which is just one polynomial evaluation. And this is all the interactive part. However, in many snarks, we cannot have this kind of like interactive protocol. So we basically use Fourier transformation to convert this interactive protocol to non-interactive protocol. So this is mainly based on like some random oracle model. So basically, in the random oracle model, we have some kind of like pseudo random generator, which can simulate a verifier. So basically, the prover will like feed some messages to this random generator, and the verifier will use this random generator to sample its randomness and do all the computation, which is known as the public key model. Basically, the sum check can be done entirely in public key. So we have the entire proof, like we take the polynomial, which is list of product of polynomial, and it can simply return proof. This proof is non-interactive, and the verifier do not need to be active when I mean the proof do not need to be active when verifying this proof. This is just like you wrote some proof on paper and then give this paper to the verifier, and that's it. So basically, in this proof function, we initialize this state and give a simulation of the verifier, and then like the prover will give the person some round and feed to the pseudo random generator, and then give it to verifier, and it will run the verifier itself, and then complete all the interaction, and then like give all the messages as a proof. And the verifier will kind of do the same thing. So the verifier will assume the prover exists. So by checking the transcript, so the verifier will first check, okay, the transcript is correct, and then the verifier will check if the subclaim is correct. And if all of them is correct, then the verifier will accept. Otherwise, it will reject. Yeah, I think, yeah, probably the Sumcheck protocol is like one of the most trivial protocol I implemented. So hopefully the structure is clear. So I think, do you have any kind of like questions on the code base? Do you have enough time?
If this was the most trivial, what was the most non-trivial protocol you've implemented?
Okay, yeah. So I'm currently working on some kind of like IOP, the interactive Oracle protocol. So do you know that, like the interactive Oracle proof? So this is kind of like a more non-trivial version than the interactive proof, because like the interactive Oracle proof needs some kind of like Merkle tree, something like that, which is kind of then not kind of non-trivial. And actually a lot of kind of like new protocol use interactive Oracle proof, such as Planck and also Aurora and Fractal. They are all using kind of like similar model, but Sumcheck is kind of like simpler because it only uses interactive proof, which is kind of like intuitive to understand.
Tom, what was the name of the protocol you just mentioned that you said was more sophisticated?
It's just like a complexity class actually. It's called interactive Oracle proof. So I believe you guys are learning from the books, right? So I think in the later chapter of the book we will kind of like study this called interactive Oracle proof, which is designed by Professor Alessandro Kaiser. So I was a student of Alessandro Kaiser, and I was learning some interactive Oracle proof here. So it's kind of like a more complex version for the interactive proof, which adds a lot of power for the verifier. But I think for Sumcheck, it's kind of like just some simple interactive proof.
What were some things that you learned in the process of implementing this? You said this was your first Rust project, and I'm sort of seeing that you used the Rust trait system fairly effectively. I see that it's sort of like scattering of generics across the code base, whether it's using your field generic over prover messages and prover state, or
Yes.
basically like talking about how the Rust type system changed how you were thinking about the protocol is sort of the question.
Yeah, so basically, I think Rust is a very nice language because it has some nice abstractions like traits and also like associated trait types, something like that, without compromising the entire speed. For example, if I was implementing this in Java, then I need to use some kind of like dynamic type lookup, which will compromise the speed quite a bit. But for Rust, everything is done in the compilation level, so I can like fearlessly use all the abstractions without compromising the speed. This is called like the zero cost abstraction. So I quite like this idea. So, and also this kind of like abstraction is quite useful in the ZK field because sometimes we just need to switch the curve. Like by default, I'm always using like BLS 381, but some people will use some kind of like other prime field. So we can just like change the field type and everything it still works, and we did not need to like reinvent it by ourselves. So basically, like when I was like implementing the Rust-based protocol, I always at least have some abstractions on the field, and we also have some like kind of other trait to check if I need to like rewrite something or not. So I think Rust is kind of like very convenient doing that. So yeah. So I think for my first project, I only do some generalization on the field, but for my some kind of like later project, I also generalize all like the cryptographic sponge or like the Merkle tree. A lot of things use abstractions, so we can write kind of like complex code in very short time. Yeah. Does that answer your first question?
Yeah, I have one. So can you talk about something about the canonical serialized?
Oh yeah.
Yeah.
Yeah. You mean for this one?
Yes.
Yeah. So sometimes like we need to serialize this entire message because we need to probably send it over the internet. So we need to do some serialization. Basically, this canonical serialized trait and canonical deserialized trait converts this structure to something in byte form, which I think is it's a trait in Arkworks. So let me show you. So if you go to algebra, let me see, it should be in serialize. Yeah. So you can see like this one is just the canonical serialized trait, which you have like the serialize method and let me see, yes, there's a deserialize one. Yeah, there's a deserialize method. Basically, for serialize, you just convert all the entire trait to some byte, which is represented like in a writer, like the byte writer. And in deserialize, you take some bytes and convert it to the field or convert it to the struct, which is kind of quite convenient when we are using some kind of like internet, or you can serialize it in the blockchain, something like that. A lot of application is using that. That answer the question?
I have a question. So suppose that you've spun up a prover and a verifier to perform some check protocol over some function, let's call it G.
Yeah.
I'm noticing that the way that you represent the polynomials received by the verifier as a vector of a field element.
Yes.
It's not entirely intuitive to me. And in my sample implementation, I ended up passing around like a wrapper around a Rust function trait that sort of I passed around dynamically, which sort of felt bad. So it felt bad. So I'm curious exactly how you did that and what sort of how that works.
Yeah. So yes, thanks for catching that. Hopefully, I need to add. Oh, sorry. Hopefully, I need to add some documentation about that. Basically, this polynomial is like a vector. So the first axis is a round, and the second axis is the multilinear polynomial. So basically, this is a polynomial in multilinear form, which is for example, now if we have like 13, 14, 15, 17, probably, yeah, and like 1, 2, 3, 4, 5, 6, 7, 8, something like that. Oh, 1, 2. This polynomial is like the polynomial sent in the first round, and this polynomial is a polynomial sent in the second round. And this one is a multilinear polynomial where this one is kind of like f 0, 0. This one is f like 0, 1, something like that. And this one is just like f0 and f1. So by using this, we can like represent like all the polynomial in this form, because the verifier only needs to use this polynomial in the multilinear form, and that's enough for them to operate. And I think there will be some caveat if you use function here, because sometimes you only have like access to the verifier. You do not have access to the prover. So in this case, using a function might have some problems, but I'm not sure if you encounter that problem, but hopefully that works. Yeah. It is clear, like the form of this function.
Yeah, that makes sense. I was able to pass around clones of a reference counted function stub so that I could have both the prover and the verifier have access to a function.
Yeah.
But I think that seems more elegant to pass around the evaluations rather than the shared access to the function.
Yeah, because like if you pass some function, then we can do more complex things. Like in IOP, it's called like the oracle, where like it's just some oracle where a black box where you query something and it returns something. It's more complex model, but we do not need to use this kind of model here, because everything is just like very elegant multilinear function, and you can represent it in a very clear way. So why not just use that? Yeah. Any other question?
Hey, you mentioned that there's like a lot of real world scenarios where polynomial commitments are used instead, or the IOP. Is there a real world scenario that you can think of for like these kind of interactive proofs where it's better suited than the prover kind of committing the whole stream and then sending to the verifier?
Yeah, yes, actually a lot. So like the interactive proof is much powerful than like pen and paper proof, like which is in MP. So basically, if you took some complexity class, you can find that interactive proof is actually p-space. So IP is equal to p-space, but MP is like much powerless than p-space. So everything you can think about in p-space can be done in interactive proof efficiently. So like for now, actually a lot of protocol is using that. Like for example, Planck, Fractal, Aurora, and Ligro, something like that. I think almost all protocol in ZK-SNARKs is using this kind of like in interactive style. But sometimes you may say, okay, it's not interactive. This is because we are using Fiat-Shamir transform, which is a heuristic where we convert like the interactive proof to non-interactive one. But in theory, everything is done interactively. So basically now, like everything you've seen is interactive proof protocol, at least. So if you want to see some concrete examples, I think in Arkworks there's a lot of applications where I think, let me see. So I think Globe 16 is also like interactive, but I'm not sure how it works. I did not implement that. Yeah, probably you can check some kind of like some examples in Arkworks to see like how they are using interactive proof in their proof protocol. There's actually a lot of things like Marlin, something like that. There's so many protocols using this kind of model. Does this answer your question?
Yeah, I think like I was wondering if there's any like real world applications to not use the Fiat-Shamir heuristic and just do the back and forth rather than
Yeah.
generating the pseudo randomness.
Let me think about that. So I think you need to refer to MPC, which is multi-party computation, where like the computation is involved in a lot of parties. So I'm not sure if any guys in ZK-SNARK is using that, but yeah, you can check MPC in Google, like this one called multi-party computation. So if you check out like this wiki page, I think you can learn more about that. But at least in ZK, I guess like everyone is using some kind of like Fair-Shamir transform style, because like non-interactive is always like better than in interactive, because like in blockchain you cannot just like wait for approval to send you message, which is like kind of like have a lot of time cost. So yeah.
There was a talk recently by Alex Ozdemir out of Stanford. He's one of Dan Benet's graduate students, where he was presenting a situation where a bunch of provers were working together over some suppose that a bunch of like credit organizations or something have some information about a user. But the credit organizations don't necessarily trust one another, so they have some secret data that's not shared that they needed to basically come to a proof about like some statement about the verifier, some statement about the person in question, that they were able to use, that Alex basically demonstrated an MPC protocol that was able to be used for a bunch of independent organizations to sort of come together and produce a statement about that particular person. But there was a paper in the 80s that basically said that interactive proofs over n rounds are equivalent to, in the complexity class, to interactive proofs over 1 round. So basically, the question reduces to, you just need to choose a large enough field such that the increase in your soundness error is offset by the increase in the field that you're choosing to do your computations over. So maybe if you couldn't change the field that you were operating over and the soundness bound grew out of hand, maybe that would be something that you could do. But I think there's probably other tweaks you could do in the protocol to adjust it back down. So I think that's my best interpretation.
Yeah, actually, there's a lot of things to learn in Sumcheck. I mean, in interactive proof. Yeah, I'm just like a student, so yeah. I still need to learn a lot from that. It's quite an exciting field. Yeah.
Good.
Actually, like I recently learned from my theory class where like you can always like represent some kind of like MP, all the questions in MP in 3 bits if you are using interactive proof, which is quite exciting. But I'm not exactly sure how it works. Yeah.
And is there a reason of the Fair-Shamir transformation random number generator is different from a generic one?
What do you mean by a generic one? What is a generic Fair-Shamir? Sorry.
So I mean just like from different from a random from a
Me a truly random generator or something like that.
from an average random generator. So just like why use a specific?
Oh, you mean this one? Like oh yeah, this is just some arbitrary this is just some arbitrary thing. Actually, I'm removing this because we now have sponge. So let me switch to this. Let me switch to this branch. Yeah, actually, I think it will be helpful if you guys can review like my latest PR, which is which is in this branch where I like changed the Fair-Shamir model. So now like we are using kind of sponge. So let me see. Yeah, we are using this cryptographic sponge, which is kind of like more robust way to like for the Fair-Shamir transform. And like a lot of guys, like for example in Planck, they are also using this sponge. So this is like more conventional way to do that. I think in the first version, like where I used like the Blake 2s ing, I'm just like using some kind of like arbitrary random generator. I did not like consider too much about that, but this time I'm kind of like being more serious. So we are using a sponge. Do you guys like know what is a cryptographic sponge?
No.
Oh yeah, so basically, let me see if I can send some message. So, is there a way to send a link? Probably I can just send it in breakout room 0.
Yeah,
Wow.
if you drop it into the Thaler book study thread, that's a perfect place to drop any link.
Yeah. A minute. Yeah. So basically, you can check this paper. This one talks about one of the sponge called Poseidon. So this Poseidon sponge is kind of like you can see this as a hash function that is optimized for ZK proof, where like the hash function takes some field element and then it will like randomly generate randomly generate some field element. So the Poseidon is kind of like the convention for almost like for almost all application now. And in this in my new PR, I'm just using some general cryptographic sponge, and the user can choose which sponge they are using, and then like use this sponge as a random oracle model to do the Fiat-Shamir. So basically, the sponge has absorbed, and the sponge can also like feed some can also generate some random messages for the verifier. So you can just think this as a very good random oracle model. Yeah.
Tom,
That's it?
what's the name of the transformation that you've mentioned a few times? Fiat-Shamir transformation. Is that right?
Yeah. Fiat-Shamir transformation. Probably I can type that. Yeah,
That'd
I'm
be
not I'm not an English speaker, but hopefully
worries.
yeah. Hopefully
We will be
my
talking about Fiat-Shamir in the next chapter, in chapter 5, by the way.
yeah, Fiat-Shamir heuristic. So basically, probably I can have some crash course now. 1 minute. Let me see if I can do that. So I think I can just do something here. Yeah, Fiat-Shamir. So basically, like, so suppose now we have some transcript like prover, verifier, and the prover, verifier. So originally, like prover is sending like, for example, M1. Verifier is sending M2, and this prover is sending M3, and the verifier is sending M4. So in order to use the Fiat-Shamir protocol, we need to Fiat-Shamir transform. We need to make sure that this interactive proof is public key, which means that the verifier randomness always depends only on the prover's messages. So now the M1 is just like some functions. I mean, not functions. Just depends on M1, and the M4 depends on like M1 and M3. So if we use this kind of like this kind of model, then we'll be good. So the Fiat-Shamir transformation just do something like this. Now the prover send M1, and the prover will like hash this message. So the prover will get some hash of M1 and feed it to the random oracle, and then like this one called RO, and the verifier will get this M2 from the RO random oracle, and then now the prover will send M3, then the prover will like update this random oracle by M1. Oh, and let me see, should be M3. Yeah. Sometimes we even like do something like M1 or M2, but that does not matter because like the hash function is kind of like it's kind of like similar to a random oracle model, so it actually does not matter. So this one will go to RO, and then the verifier will get M4 from the random oracle. So basically on the approval side, the approval will run this verifier by itself because like the verifier only depends on like the messages and also the random oracle. And then like the approval also run the verifier by itself, so we can do this like non-interactively. And now the verifier have the entire transcript, so the verifier can also like simulate this approval by itself, like run the random oracle, and then like generate this message to check if the transcript is correct, and then do the main check. So like the approval will like simulate a verifier, the verifier will simulate approval, and all of them can be done like independently. Is that clear? Or I can probably speak more about that.
Clear enough for now, I think.
Yeah.
Could you further explain how the random oracle works?
Oh yeah, okay. So basically, so let me probably, yeah. So we have like a random oracle struct. So basically we can just call like some struct random oracle. And then this random oracle will have like let me just be freestyle. Yeah, this random oracle will have like two functions, like which is called like let me see absorb message, and this will have let me think about a good name. So let me see what sponge is doing. 1 minute. Yeah, squeeze. Yeah, okay, squeeze. So yeah, to be more rigorous. This one will have some like message. So this random oracle internally will have some state. So for Poseidon, we have like some kind of like field elements as state, but it's not always true for all the random oracle. So basically every time when you absorb these messages, it will update this state, and when it squeezes the messages, it will also update the state. So like all the randomness depends on what the messages you are absorbing and what the message you are squeezing. So basically, you can think about like the absorb as an input where you update the state for the random oracle, and the squeeze is just some output for the random oracle. You can squeeze like any number of elements you want, like elements, but yeah, it's not necessary. So kind of simple, right? Like just some squeeze, yeah. And
Yeah.
if you want to check more about that, I suggest this repo. So this repo is also written by me and William, which is also who is also in Berkeley. So cryptographic sponge, and I can send a link. 1 minute. Let me see. Yeah, the sponge. So I think you can check. This sponge will have like the Poseidon sponge and also some RCS constraints for the sponge, and yeah, you can see that it's just some commentary. You have some new config, absorb, squeeze bytes, squeeze bits, squeeze few elements, something like that. So it's kind of like similar to this interface. Yeah. So if you want to learn more about that, probably we can schedule another meeting because like this sponge is also written by me. So
Hi, earlier you were talking about the encoding of your polynomials. Could you elaborate on how you evaluate the polynomial in one variable so that you get a multivariate polynomial of 1 degree less? Degrees of
okay.
one variable.
Yeah, sure. So basically, like for Sumcheck, just some crash course. So like when the prover is sending, like for example, let me see, the prover is sending like x1, x2, x3, x4. Let's see. So this one is a polynomial over 4 variables. So it is represented by a array of like 2 to the power 4, like hypercube, and the verifier will first sample like r, like this one is a randomness. Sorry, GitHub compiler is crazy. Yeah, sample some R, and then like it will like first evaluate like f0, x2, x3, x4, like f1, x2, x3, x4. So it will first like put the degree down by one variables, and also it will evaluate on like R, x3. We want to check for consistency. So basically, it checks consistencies from like those two, f0, f1, to make and it will interpolate it, and then like get this new polynomial. So basically, this interpolation is in this function where there's kind of like interpolate poly. So it takes some evaluations of this polynomial and evaluate as this R, and it will return some kind of like the evaluation, I believe. Yeah. And for this one, I think, yeah, it's written like quite a while ago. Yeah, it's just some like Lagrange interpolation, no fancy stuff. I think it's not even optimal. It's good time. So I think probably if we want to optimize it, we can use FFT, but it's a hypercube, so I did not come up with a very elegant solution using FFT. So I think that's enough. Like the speed is not compromised too much. So this one is the function you want, like the evaluation on the hypercube. And
Thank
by
you.
the way, it's in verified.is, so you can check more about that.
Would FFT technically speed that up at all, since it's such a small?
Yeah, I don't think
Yeah.
FFT will speed it up, but I'm hoping it will come up with some kind of like speed up. But FFT always like in my experience, I always do some FFT on like multiplicative subgroup. Like we have kind of like a concrete domain, like we have a generator, and we have like some FFT domain where like you can reuse some computation on like on the cyclic subgroup. But for Sumcheck, we are just doing them on some naive hypercube. So I'm not sure how to use FFT to do that. Hopefully we can do that, but I need to like learn more about that. But I think in this case, simple Lagrange interpolation is kind of enough. But I believe there will be kind of like better way to do that. By the way, this is the only time we we treat this not as an array as a polynomial. For all the other time, it's just like always represented in multilinear form, which is like quite elegant form.
Cool. Well, if there are no more questions, let's sort of start wrapping up. Thanks everyone for coming, and thanks Tom Shen for coming on today and presenting your library.
Thank you.
So, thanks everyone for coming.
Thank you. Have a good day. Bye.